Hey, it's Justin here again, and this is. Chapter 2 Newtonian Mechanics. To analyze particular interactions within any process, you must first choose a system object, which is the object you choose to analyze the forces acting upon it and observe its motions. A force is a physical quantity that characterizes how hard and in what directions an external object pushes or pulls on the system object. It's represented in newtons and in the force diagram, which we'll go over shortly. An example of the force is you pushing a motionless box forward to the right with x newtons of force. The box is the system object while you're the external object. You're exerting x newtons of force on the box. To the right is a force diagram. A force diagram is used to display the forces acting upon an object. In this case, this person here, we'll just name her Jill, I guess. Jill is holding a ball right here. The ball, the system object, in her hands. Stationary. Therefore, the hands of Jill on the ball are exerting the same amount of force as the force the Earth exerts on the ball. The Earth pulls downwards on any system object at all times towards the Earth's surface. This is primarily called gravity. Adding forces would result in finding which direction an object is moving, as well as what amount of force is being exerted on that object. This is called the sum of the forces. Horizontal forces are added separately from vertical forces. Basically, the sum of the forces is the resulting motion in a system object. These are the equations for the sum of the forces equations. Top one for horizontal forces, and the bottom one for vertical forces. Acceleration is proportional to forces. The higher the force in that direction, the higher the acceleration. An object's velocity points in the direction of the sum of the forces, as well as its velocity change. An object with a small mass has a bigger acceleration from the sum of the forces, and an object with a big mass has a smaller acceleration from the sum of the forces. This phenomenon can be described in this equation. Acceleration equals the sum of the forces on the system divided by the mass on the system. Equals mass. Newton's third law states that when two objects interact, Object 1 exerts a force on Object 2, and Object 2 exerts a force on Object 1 equally in the opposite direction. Basically this. Now, let's move on to a practice problem. Problem 6. You throw a ball upwards. A. Draw a motion diagram and two force diagrams for the ball on its way up and another motion diagram and two force diagrams for its way down. B. Represent the motion of the ball with a position versus time graph and a velocity versus time graph. First, a sketch of the situation. This is the motion diagram for the ball going up. The velocity begins to decrease as the ball moves up, since gravity, over time, is slowing the ball down. This is the force diagram for the ball upon release. The up arrow, aka the force hand on ball, is larger since the resulting motion is up. This is the ball after the release. Only the Earth's gravitational force is acting upon the ball at this point. This is the ball's motion diagram at freefall, going downwards. The velocity increases negatively. Gravity / the Earth is speeding the ball towards the ground. This is the force diagram during freefall. Only the Earth is acting upon the ball. This is the force diagram of the ball hitting the ground. Assuming the ball bounces, the force of the ground on the ball will be greater than the Earth's force on the ball. This is the position versus time graph for the ball. It goes up from the ground down to the ground again. Let's assume the ball was thrown from the ground. This is the velocity versus time graph for the ball. The velocity continually decreases over time. We're also ignoring the moment of impact when the ball hits the ground, in this graph. Yay, problem solved! On to the next chapter.